All right, so today's lesson, Foundations of Math 30, from the Nelson Foundations of Math 12 textbook. We're on 5.5, talking about conditional probability. So we've talked about probability of independent events. We did that last lesson, 5.6. We actually jumped ahead. So you know about independent events, and I contrasted dependent events as well. But I just want to take a closer look at what dependent events are. So dependent events are events whose outcomes are affected by each other. If you remember the example from yesterday, talked about Josh's decision to go to 7-Eleven to pick up a coffee before school this morning, and Ben's decision to go to Tim Hortons. If they know nothing about the other's plans and don't care at all to have coffee with each other before school, those are independent events, right? Josh's decision is not based at all on Ben's decision. But if these guys are good buddies and they generally have coffee before school, Josh might call Ben and say, hey, where are we going for coffee this morning? And Ben say, well, I really wanted to go to Tim Hortons. So that would affect Josh's decision. Those events are dependent upon each other, right? So those are dependent events. Another example, if you draw two cards from a deck of cards without replacement, and we need to talk about this here. Let me just highlight that for you. So drawing two cards from a deck without replacement. So that means you have 52 cards in a deck, right? And then on the next draw, you have how many left? If you don't put that card back in that you've drawn, we have 51, right? So if we're talking about an example of, let's say, what's the probability that we would draw a red card? Well, you would say that's 26 out of 52. But what's the probability that we would draw two red cards in a row without putting the first one back? That is a conditional probability. Now look at this. The conditional probability is the probability of an event occurring given that another event has already occurred. That's conditional. And you guys know about conditions, right? There are lots of conditions on, let's see, we just moved this last fall, and there were conditions on our sale. That means things that had to happen first before everything went through. So when we're talking about conditional probability, that means what is happening before this, like that's affecting what's happening now. So we have 26 out of 52 chance of drawing a red card on the first draw. On the second draw, there's one fewer card in the deck, so that's where 51 comes from. And there's also one fewer red card if we've assumed that we've drawn one already. See that? So this is not a real stretch for you, I don't think. This is fundamental counting principle stuff, right? You have two decisions to make. You're drawing two cards, and you just take a look at each draw, and what are the chances of this happening. So that's conditional probability. And of course, you'd multiply those out, and you get the probability that you would draw two red cards. So that's an example without replacement. Okay, those are dependent events, and that'll show up a little bit later. But let's go back to the textbook here, and I want to do this first example with you. So if you take a look at example 1, calculating the probability of two events. So here's our third example, I guess. We did the guys going for coffee. We did some cards here. Let's talk about this one now from the text. All right, determine the probability that Jocelyn will draw two defective chips. And I guess what I didn't copy over is that when they're making computer chips, they're assuming that 3 out of every 100 will be defective. Okay, that's their guess, and you can't be perfect all the time, right? So they're guessing that there's going to be 3% of them are not going to work, but 97 will. And so she's going to draw out of a big bucket of these things. She's going to draw two computer chips, and this question says determine the probability that both of them will be defective. Okay, so you might have an idea already on how we're going to go about that. Here's the first chip, and then here's the second chip. And because we're drawing two, we need to multiply the probabilities, right? This is not an or, not one or the other, it's and. It's the probability of a defective chip on the first one and defective on the second one, right? That's what we're looking for. So if we go back to the card example here, right? I shouldn't erase that. What's the chance that we're going to have a defective chip when all of them, all 100 are in the box, What's the probability that we're going to draw a defective one? 3 out of 100. Yeah, it's right there. Okay, so 3 out of 100. So that goes in the first. That's chip number 1. So if I'm trying to find the probability that both are defective, I have to assume for this one that the one I've already drawn is defective, right? So you tell me now what probability, what fraction am I going to put in here? Yeah, nice and loud. What? 2 out of 100? Okay. Agree with that? Okay, now, did I put that chip back? No, I didn't put it back. So that would be like without replacement, right? Okay. Good guess, and I'm actually glad we got something wrong because this is a good teaching moment. Everyone notices when we got something wrong. Okay, so what should go here then? 99, yeah. See, we've got one less defective chip, and we've also got one less chip in the box. Make sense? Okay, not that hard, right? Conditional probability, not that bad. All right, so we multiply those together, and then, yes, we should get our probability. So what is that in simplified terms? What do we get? 6 over 9,900. And what does that boil down to? 1 out of 1650, something like that. Okay, so there's a very slim chance that 2 in a row will be defective. But what I want to do, and in this section, I'm going to try and tell you how to do these questions really without messing around with the formulas too much, because the formulas can be a bit tricky, and students get tripped up on the formulas all the time. So we're going to do fundamental counting principle like I just did here. We're also going to do tree diagrams, but I want to show you the formulas, okay? Because really this, what we just did here, this fundamental counting principle sort of idea, is the first formula. So we wanted to find out the probability of drawing 2 defective chips. And what we did is we took the probability of pulling the first defective chip, okay, right? That's what we did right here. And then we multiplied that by the probability that we would draw a second defective chip. And this is where the new notation kind of comes in. And there's a straight line up and down here like this, given that the first one was also defective. So there's your formula. And really that's just what we're doing when we think about multiplying probabilities. Okay? So that's the formula. And you know, I think they write it with A and B and B and A here in the book. But that's really what we're doing. So you know these are dependent because this one, right, this has changed. That one has changed from the first one. If we threw the chip back in and it wasn't a conditional probability thing, I would go 3 over 100 times 3 over 100, right? Those would be then independent events. So you see the difference? This is independent. This is when I put the chip back in the box. And this is dependent when it depends upon what I did the first time because I'm not putting it back in. Okay? So I know there's a lot going on here, okay? I get that. So I hope you guys are ingesting all this and just processing. But it's not that hard. But I am going to do the tree diagram. I'm going to do a tree diagram example for you. And we're going to skip to example 3 in your text. So if you could kind of go back to your text a little bit there. And let's take a look at example 3. Example 2 is a good one too. I'll get you to look at that one on your own a little bit later. It's using Venn diagrams. Makes a lot of sense too. But I'm going to skip that one for now in your text. But, whoops, where is example 3? Is that example 3? No, that's 2. There it is. Okay. Okay. So this one right here, I'm going to show you how to use the tree diagram. And yeah, I know tree diagram sounds like something that's pretty elementary, but you know what? It's very, very helpful. And I like doing the tree diagram, so you can do the tree diagram too. Don't feel bad. So let's put that puppy here in the notes. Okay. So this one's pretty easy too. The tougher questions are going to come a little bit later in the lesson, but this is pretty easy. But let me show you how to do the tree diagram as well with this one, okay? So according to a survey, this says 91% of Canadians own a cell phone. Now, I don't know when this was, but probably pretty close to what it is today. Of these people, 42% have a smartphone of some type, okay? So 42% of the 91%. You can probably already see where we're going here. Determine to the nearest percent the probability that any Canadian you meet during the month in which this survey was conducted would have a smartphone. So we're trying to figure out of a random person, would they have a smartphone? What are the chances? And so I'm going to show you the tree diagram here. So this one's going to go, okay, cell phone, okay? There's two options, people that have a cell phone and people that don't have a cell phone. And if we look at the probability, this is 0.91 that they're going to have a cell phone. This one is 0.09. Okay, so that's our first step. So if we stopped right there, you would have a 91% chance, right, of meeting someone that has a cell phone. But now we want to find out what are the chances of you meeting someone that has a smartphone. So from here, tree diagram, if they have a cell phone, there's a smartphone and not a smartphone, dumb phone. Okay, what are the chances there? Well, 0.42. You put your probability right there. And this one, if you care, right, 0.58. You can always do that. Remember, they have to add up to 1. And so this question says, what's the probability that you'll meet some person that has a smartphone? And so we can find out this probability. This is a cell phone and it's a smartphone. And this probability right here is cell phone and it's not a smartphone. And if we care, this one right over here is the probability that we don't have a cell phone, right? Which is already done for us. But what are we interested in here? We're interested in this probability right here. And so we multiply the parts of the tree that lead to that. We multiply those to get that right there. And I think you guys have all done this before. But anyway, so you go 0.91 times 0.42. Multiply those together. And you get your answer of 38.2%, so about 0.3822. Okay? So, yes, we could have done the other method as well, which would be 91 out of 100 for the person having a cell phone times 42 out of 100 for the person having a smartphone of those people, and that's the same thing, right? But I wanted to show you how the tree diagram works. Because finally, the final example I'm going to give you here in the lesson is example 4. And this is where I think the tree diagram is going to help us out quite a bit. So right now, this has just been dependent events. It says conditional probability problem, but that's pretty low level. So let's take a look at our final example from the text, example number 4. Right here. Okay, making predictions that involve dependent events. Okay, so here's where it gets real here. We're going to use a tree diagram. Don't have to worry about formulas again. Just tree diagram's going to work right here. Hillary's the coach of a junior ultimate frisbee team. Based on the team's record, it has a 60% chance of winning on calm days and 70% chance of winning on windy days. So we have two things here that we're going to consider. 60% chance on calm days, 70% chance on windy days. Tomorrow, there's a 40% chance of high winds. Okay? There are no ties in ultimate. What's the probability that Hillary's team will win tomorrow? So this is a different kind of question. You can't just go multiplying percents here, right? Because this is a bit different. So we want to consider this. In this type of question, what's the probability that Hillary's team will win tomorrow? Well, we have to consider the factors that are involved, right? Is it going to be windy or is it going to be calm? And if it's calm, what's the chance that they still might win? Right? There's a lower chance that they'll win, but they still might win. So we're going to have to figure out what the probability of calm and wind. We're going to have to find out the probability of windy and wind, right? And so that's like case 1 and case 2, right? Or here's the probability of winning on a calm day, and here's the probability of winning on a windy day. Those are kind of two separate things. We have to add them up, right? Because it's one or the other. So just looking ahead, that's what we're going to be kind of looking at. So let's do our tree diagram. Let's get to it. All right, so there are two chances for the weather conditions tomorrow. And just got to get to my question here. Okay, so two chances that we could have. So it's going to be either windy or it's going to be calm. Okay, and so it says that there's a 40% chance of high winds. So tomorrow the conditions are, this is 0.40. There's a 40% chance that it's going to be windy. And so that means that there's a 60% chance that it's going to be calm. Okay? What else are we told here? Okay. Based on the team's record, there's a 60% chance of winning on calm days. Okay, so if it's calm, right? Now this is how the team's going to do here. So they're either going to win or they're going to lose. WI. All right. So on calm days, they have this is calm, they have a 60% chance of winning. So I put my probability there. So again, tree diagram, put your probabilities on each of the branches. So that means that they have a 0.40 chance of losing. Okay. On windy days, they do pretty good on windy days, looks like. They have a 70% chance of winning on a windy day. So they could win or they could lose here. And the chance of winning on a windy day, okay, so it's windy already, so what's the chance that they're going to win? Is 0.7. That means that they have a 0.30 chance of losing that day. Okay, everyone with me so far? Just fill out your tree diagram. Are there any other factors in the question that we're considering? It's just windy or calm, right? And then their winning percentages. So there's nothing else, we're not taking any else into account. So, what are we going to get here? Well, we are going to get the probability of windy and a wind over here. That's what this one's going to give us, right? This branch and this branch. Down here, this one's going to give us the probability of windy and a loss. This one's going to give us the probability of calm day and a win. And down here, this is going to be the probability of a calm day, but they lose. Okay, so you fill out the tree diagram, and the question says, what's the probability that Hillary's team will win? So which one of these probabilities have wins in them? Well, there's a win, and there's a win. So if we find out the probability of these two, right here, and then we add them together because it's win on a windy day or win if it's calm. You see that? So it's a win on a windy day if or a win on a calm day. So when there's an or, then you add. Okay, so it's this one or this one. Okay, so we need these two probabilities. What are they? 0.4 times 0.7. What does that give us? 0.28. And over here, 0.6 times 0.6. And that's 0.36. So do you see where I'm getting that from? Right? 0.4, 0.7 gives us 0.28. And 0.6 and 0.6 gives us 0.36. So finally, if we're going to take either of these consideration here, so the probability of a win, just in general, is 0.28 plus 0.36. So that's 0.64. So that's the probability that they will win tomorrow. Right there. So that one's a bit of a next level question there, right? But the tree diagram really helps us out with that. And like I say, there are There's one other formula, but honestly, you can take a look at it and ask me about it if you really want to use the formula. There are definitely places for it, but this will get you 95% of the questions that you need to do. And the tree diagrams, fundamental accounting principle, understanding what independent and dependent events are, that's going to do it for you. Okay, so I'll just show you the review notes here while I give you your assignments. So there you go. Just take a peek at those. So here technically is the other formula that we didn't use. It's just kind of a rearrangement of this formula. So anyways, it's just a rearrangement of this first formula that I gave you.